Hello, everyone. Welcome to the presentation of Self-Building Data Center Network. My name is Yan Cai. I am a software engineer in the network infrastructure team at Facebook. Today, I'm going to present the effort we made at Facebook to facilitate the data center network design and the deployment process. The title of the presentation, Self-Building Data Center Networks, indicates our intention to build the automatic network deployment process. Typically, a data center deployment process consists of 4 phases: planning, design, deployment, and turn-up. Among them, network topology is the critical piece of data. My talk will be focused on the design of the network topology. Facebook owns and operates one of the largest global network infrastructures in the world that serves billions of users on a daily basis. To meet the constant growing demand in the network capacity, we keep building new data centers as well as upgrading existing ones. At the end of the last year, we announced that Facebook had 15 data center regions globally. In each region, we have several data center buildings. Each of them hosts a data center network. In addition, there is a fabric aggregation network that interconnects the data center building as well as the internet. It is challenging to make network deployment that keep up with the growth in capacity demand. First, data center build-out is a long process. Starting from selecting a location, it can take months or even more than a year to complete an entire project. Second, it involves many teams working together on different tasks, including power, cooling, network design, server rack placement, fiber installation, and cabling, as well as traffic testing. Third, live traffic network migration requires a sophisticated migration procedure, which significantly increases complexity of the deployment process and hence slows down the progress. Like many other owners of big network infrastructure, we also believe that automation is the solution to grow network capacity in a sustainable and efficient way. However, on the other hand, as many of you have known, it is not easy, sometimes even impossible, to achieve a fully automatic deployment process. Our strategy is to start with a hybrid process, mixing of both manual and automatic steps, and gradually automate more and more steps over time. On the left corner, we aim to show that the network topology is used throughout the 4 phases of the deployment process, including planning, design, deployment, and turn-up. In the planning phase, based on the prediction on the growth of bandwidth demand, we make decisions on where a new data center should be built or which existing data center should be expanded. In the design phase, the design of the data center building, including power, cooling, and the network, will be finalized. In the deployment phase, server racks are placed in the data center building, and fiber switches and routers will be installed. After all the equipment is installed, the turn-up process starts. Cable QA, device health check, and the traffic testing are conducted. If everything goes well, the production traffic will flow through the new network infrastructure. The network topology is used throughout such a long and complex process. In the planning phase, the network topology is used to determine the count of the devices and parts to purchase. In the design phase, the network topology architecture affects the building floor plan design, which in turn determines installation of power and cooling facilities. In the deployment phase, a combination of network topology and the server rack locations decides how to place fiber throughout the data center building. In the turn-up phase, the end-to-end connectivity of the net topology is verified. By nature, network topology can be modeled as a graph consisting of nodes and edges. The picture in the middle of the upper layer illustrates that the same network topology can be modeled at a different level. The closest model is one at the layer and domain level. In such a model, every node represents a network layer or a domain in the data center network. The layer could be span, leaf, and tall. The definition of a domain is more flexible. It could be a pod or a span partition. The edges among the nodes are the inter-node bandwidth capacity. This kind of model is usually used to design the high-level routing policy. A finer-grained model can be defined at the device level. Namely, all nodes in the graph represent switches and routers in the network. Correspondingly, the edges among them are the links that interconnect the devices. In this model, the names of the endpoints of links are generic. Namely, they don't have to match with the true interface name. Such a model is used to evaluate the capacity of the network topology. The most granular model is a network graph consisting of real devices and port names. This kind of model is called the port-level model. It can be obtained only after all hardware platforms of all devices have been finalized. It is because in our heterogeneous data center network devices of different vendors follow different naming conventions for the ports and interfaces on those devices. This model is required in building physical paths among the devices and generating switch configurations. How do we generate a net topology? Given the scale of a data center network, the topology can only be generated programmatically. As shown in the picture on the top right corner, a data center network topology is usually designed according to certain sweeping rules which regulate basic properties of the network. For example, in the pod, every leaf switch is connected to every port, forming a complete bipartite graph. The same pattern is also replicated between the span and the leaf switches within the same span partition. For such simple sweeping rules, it is relatively easy to codify them and hence generate a homogeneous data center network. The scale of the network in terms of the number of devices in different layers is configurable. As sweeping rules get more complicated, it becomes harder and harder to codify them. At Facebook, we support net topology with a complicated sweeping rules via graph decomposition. In particular, given a non-standard topology, we compose it with a multiple basic network blocks, each having a well-defined structure. We claim that any irregular graph can be split into a number of such basic blocks. The more irregular the graph, the larger the number of blocks would be. In practice, we now rely on humans to do graph decomposition, which is quite effective for supporting all existing use cases. If sweeping rules get extremely complicated, then it eventually becomes impossible to codify them. In such a case, we need to seek other solutions. Apart from how we generate a network topology, an equivalently important problem is how to represent the topology generation request. It is the input to the topology generation module. At Facebook, we invented a Swift-based network model to characterize the high-level statistics of the network topology. Even with its own limitation, the network model works quite well for existing and future network topology design. The topology generator we mentioned above has been used to support all use cases. It's showing in the picture on the left side of the bottom layer. The supported use cases include both greenfield and the brownfield deployments. The term greenfield refers to a deployment task where we build the brand new network from scratch. In contrast, the term brownfield represents all other types of tasks where incremental changes are made on top of existing network infrastructure. Typical brownfield deployments include addition of a new set of racks and switches, and the replacement or upgrade of a portion of existing network. It is well known that network migration is quite challenging. First of all, while we conduct network retrofit and migration tasks, lab production traffic is still flowing through the network infrastructure. We have to be very careful not to introduce negative impact on the lab traffic. To do so, we design sophisticated migration steps and executed them in strict order. What's more, during the migration process, we often need to design and utilize non-standard transient network topologies. For instance, when upgrading a fabric aggregation layer, we often want to connect new devices to the same set of ports on the backbone side that were connected to the old devices. Here, I would like to take the chance to present a use case where we rapidly enable deployment of additional backbone to data center capacity in response to the traffic surge at the early stage of COVID-19 outbreak. In March, the lockdown policy enforced by many local and national governments caused increased engagement and use of Facebook platform. To handle suddenly increased traffic volume from backbone, our network team needed to quickly deploy more network capacity between the backbone and the data center. Due to the limited availability of free ports on the backbone side, we couldn't afford to extend our symmetric fabric aggregation layer uniformly. As a result, we decided to patch two small uniform networks. However, such expansions caused the overall backbone to data center network to be no longer uniform. We applied the graph decomposition approach to break the asymmetric topology into several uniform ones and generated them separately. In the meantime, we also encountered another issue caused by the lack of stripping rules on the backbone routers. We adopted a solution that our topology design engine directly uses a set of backbone ports specified by the network engineers. From the past, we learned a lot of experiences and lessons. Here, we share some of them, which are listed on the right-hand side in the bottom layer. First, it is important to keep a single source of truth throughout the life cycle of the network, during which the source of truth can exist in different forms. In the design phase, it is the network design intent which specifies the high-level characteristics of the party network, as well as the stripping rules used to create a network instance. Once a network instance is created, it is stored in the permanent storage and becomes source of truth for the rest of the data center management ecosystem. Second, the topology generation mechanism needs to be deterministic and repeatable. The topology design system should be subset giving the same input, namely the network design intent. The output is always the same. To achieve this goal, ideally, the topology generation mechanism should be stateless. However, on the other hand, in the network expansion use case, it has to be stateful. As shown in the above example, when adding new backbone to data center capacities, The existing fabric aggregation network has to remain unchanged. Such stateful topology generation mechanism really makes it difficult to completely reproduce the final state network topology in the future. Third, simplicity is our friend. A simple network topology not only facilitates design and deployment, but also eases maintenance and troubleshooting. In particular, we have been trying our best to preserve uniformity of the network as much as possible. On the other hand, there are still certain non-uniform topology architectures we have to support. We take advantage of the graph decomposition and the software abstraction to handle such use cases. Last but not least, network infrastructure keeps evolving, which requires constant revisions to the deployment workflow. As a network deployment task typically requires multiple teams to work together, it is critical to keep communication channels open among all the stakeholders. Even though execution automation can help reduce human interventions, it is still beneficial to design and revise the workflow in advance and review it with all partners before start of the deployment task. Any questions? I'll be happy to answer a question. Here is a question. What kind of automation tools do you use? At Facebook, we own our own automation tools. Thanks for Sunil to addressing that question. In your experience, are you able to quantify the differences between the work and time distribution between the automation and the manual, considering repeatability? As we need to deploy more and more data center capacity, we see repeatedly, the repeatable work. So this motivates us to develop the automation platform. And we believe this automation platform will significantly reduce the human burden. There's another question. What are the problems do you see in using tools like Ansible? I think Ansible represents, a open source IT automation tools. So given the scale of the Facebook network infrastructure, we really have challenges in integrating the open source tools into our own platform. And usually, it's the most efficient way for us to build our own tools to manage large scale of our fleet. Thanks, everyone. This ends my presentation. If you have any questions, feel free to reach out to me or Sunil for further communication. Thank you very much.